little bit about eigenvectors. And an eigenvector, by definition, is an eigenvector of a linear transformation, is a non-zero vector v such that for some lambda, a real number, mv equals lambda v, which is to say that an eigenvector of a matrix is a non-zero vector whose direction is not changed by m. And the value lambda is called the eigenvector's eigenvalue. And a very important fact is that eigenvectors are all orthogonal to one another. And so one of the ways to think about these high-dimensional linear transformations is to think about what a surface looks like that satisfies, so for any point on that surface, v, a vector is pointing from the origin to that point, that mv is a constant. Well, when m is positive definite, then those points form a hyperellipse, and the eigenvectors are the axes of that hyperellipse, and that's very helpful to think about at times. Okay, so let's look at some of the eigenvectors that come out of this process of computing the eigenvectors of the Laplacian of the graph that we've developed. Okay, so let's look at some of the eigenvectors that come out. Because of the way we've set up the Laplacian, when we order the eigenvectors by increasing eigenvalue, which would be the normal way to do things, the eigenvector with the lowest eigenvalue, well, that lowest eigenvalue is 0. And the eigenvector corresponding to it is not of interest to us. It only reflects the frequencies of words in the corpus, and that we already know on the way in. So it's the next eigenvalues and their corresponding eigenvectors that matter to us. So the one that we're not looking at, I'm calling the zeroth eigenvector. This is all very standard stuff. And then the next one is eigenvector number 1. So we can look now at this eigenvector, and here is an example where we're operating in a universe where there are 1,000 dimensions. The 1,000 most frequent words in this corpus serve as the basis, basically the set of axes for the system that we're looking at. Basically, the space, k is 1,000. It's the space in which the vectors that we're looking at live. All right, so here we are, and you can see that, well, what can you see? So we've got, I've written down here the 15 words that correspond to the lowest coordinates, 0 through 14, and the 15 words that correspond to the highest value. Okay, but here now is there's some counterintuitive stuff. I've mentioned this already. I'm going to say it again. It is still going to sound kind of crazy. So this eigenvector is a vector which has 1,000 coordinates. It's a vector, after all. It has coordinates. And each coordinate corresponds to a particular word. That's the 1,000 different dimensions of this world. So this vector has all these coordinates, each of them corresponding to the world. And now we sort those coordinates, which normally wouldn't make any sense to sort the coordinates of a vector. What could that possibly mean? But the point is, because of the mathematics we've done, we know that these eigenvectors have the property that they give coordinates to words that are, it gives coordinates that don't differ very much to words whose behavior is very similar. Okay, so, yeah, actually, there's one more thing I need to say about that eigenvector, that zeroth eigenvector. The zeroth eigenvector assigns all positive numbers to all the coordinates. Okay? Actually, footnote, sometimes it can go either way. They can all be positive, or they could all be negative, because if you multiply an eigenvector by -1, it's still the same direction, and it's still an eigenvector. So in any event, the zeroth eigenvector, let's say it has all positive values, but because all eigenvectors are orthogonal to one another, let's look at the zeroth and the first. The zeroth has all positive. The vector of the zeroth eigenvector has all coordinates that are non-negative. Therefore, the coordinates of all the next whole bunch of eigenvectors have to have positive and negative values, such that when you take the dot product of a later eigenvector with the zeroth eigenvector, the result is 0, because eigenvectors always have to be orthogonal. There's a footnote there too. They have to be orthogonal, but it's possible for there to be, in principle, it's possible for there to be 2 or more eigenvectors that have the same eigenvalue. In that case, we have some choice as to exactly which direction do we pick for our eigenvectors, but that's not going to happen for us. That's a mathematical possibility, but it isn't a real-life possibility. All right, so I've just explained why it is that we will see a balance of positive and negative values for the words, for the coordinates of the words in our eigenvectors. And so now we're looking at eigenvector number 1, and we see a bunch of words. Here they are: world, problem, family, car, state, same city, way, man, church. And you probably say to yourself, what do these have in common? Well, so they are nouns, yes, and they are high-frequency nouns, high-ish frequency nouns. And we look at the bottom of that eigenvector, and what do we see? Number 999 is in, and then going upwards from there, to, the, of, for, and, on, that, a, with, was, at, is, as, and had. These are what linguists would call grammatical words. They're not content words. So what the first eigenvector has pulled apart is it's put lexical words at one end, in this case all nouns, to me surprisingly, and at the other end it has put all of these high-frequency grammatical morphemes. So that's, in a sense, the biggest contrast that this eigenvector decomposition notices. All right, let's move on to the next. Here's eigenvector number 2. And what do we see here? At one end, you've got the words the, a, his, this, it, that, to, in there. Okay, so what do we see? In the first 4 items, we see words that could begin a noun phrase. The, a, his, and this could be followed by a noun. It also begins a noun phrase, but it also ends that noun phrase. Nothing follows it inside. It just replaces, or it stands in the role of an NP. That, to, in don't fall to under the same generalization. Okay, looking at the other end, we have, be, get, take, may, do, see, find, give, know, go, say, tell, think, bring. What do we see? These are all the null forms, the null suffix forms of verbs. These are all verb stems. They become verbs by adding a null suffix. Okay, well, so this eigenvector decomposition on the eigenvector number 2 is pulling these out and saying these should be tightly together. These should have values assigned to them on the eigenvector, which are close to one another. And of course, if we went higher, 984, 983, and so forth, we'd find more. All right, on to the next, eigenvector number 3. What do we see? At the top of the list, we have would, was, could, had, is, can, must, has, must, say, should, might, will, did. So it's finding a lot of similarity between these words, and these are the words that can invert in a yes-no question, like would you do it, was he there, could he do it, had he done it. They're also, perhaps more importantly, the words that can be followed by not, I would not, I was not, I could not, I had not, he is not, he cannot, and so forth. So there are a number of distributional characteristics that this analysis is saying are important. At the other end, we have the, his, her, this, their. So these are once again our prenominal determiners, followed by some non-zero forms, some infinitival forms. Okay, I think that's the end of the. No, there's one more. Okay, the next eigenvector has of, and, into, for, with. So other than the and, these are prepositions. The first several. Number 6 is not, from, by, on, into are prepositions. Okay, so this is a kind of a mixed bag. At the other end, you have taken, made, done, given, told, brought, been, asked, held, called, said, obtained, and then doesn't fit very well, expected, sent, presented. Okay, so one of the problems that I started doing this to solve was, how do we find a way to automatically determine those words that syntactically have the same behavior as ed suffixes? And so here in eigenvector number 4, this decomposition is suggesting that it's going to pull these words together, give them similar coordinates, which is to say, put them close to one another in this embedding. And I'm pretty sure this is the last slide here. Oh no. Okay, here's the 10th eigenvector. At one end is them, him, me, himself, years, may, God, dollars, can, should. Looks like a whole bunch of things that don't share a lot in common. At the other end, likewise, the, health, highway, a, had, got. Not much. Okay, so why did I put that in? So when I first started doing this was, I don't know, 10 years ago, I got these eigenvectors out, and I didn't have any reason to expect that the results that would be of interest to me would be at the one extreme or the other of the eigenvector. And it was a surprise. In the high-valued eigenvectors, that was true. But once we get down to eigenvector number 10, this effect disappears. And I needed to find a way to see it all in one blow, so to speak. And so that was when I started thinking about constructing a graph and then visualizing the graph. Anyway, so these are typical results that come out of looking at the details of the eigenvector decomposition of the data that arises in the way we've just been talking about. All right, I want to look at some results with you. I'm going to start with two visual illustrations of all of the words in the Encarta Encyclopedia. The first one is for English, and what you see here is kind of a big blob. As we look at words on the edges, we see some generalizations. We've looked at that a little bit earlier. We'll look at some more. So yeah. Okay. In here is French. Again, I think we looked at that a bit. You can see how various important grammatical categories are pulled out. Prenominal modifiers, plural nouns, not distinguishing masculine and feminine. Oddly, up here, the feminine singular nouns, names of cities, and so forth. Okay, we've looked a bit at that in detail. What I want to focus on here now is what we get if we look at small neighborhoods around words. Okay, so remember what we've done. We went from that original data that was in a matrix. We used spectral embedding to put words into RK, where K is 10. And then from that, we constructed a graph of nearest neighbors where we chose how many of the nearest neighbors to use. All right, so here what we're doing is, what I did was I took a particular word and used it as a seed word. So here the word is called. So you see it's in orange and boldface. And what I wanted to do was, for a given word called, and I chose that because it's like jumped and walked. It's just a standard normal word. It's a verb that takes ed for its past tense form. And I wanted to see what words had similar distribution. So I chose the 5 nearest neighbors, and they're in blue. And you can see what they are: established, caused, joined, brought, and considered. And then for each of those 5 words, I asked, what are your closest words? And you see them here. Established has those, well, you see, discovered, founded, formed, created, and considered. In any event, so this is 2 generations of nearest neighbors. And you can see that most of them take ed as their suffix. A form like named would be analyzed by linguistics as having a d suffix, and carried would be analyzed as having an ied suffix. Okay, so these are all, this is a way of automatically determining that different forms, different morphological forms, play the same syntactic role. Okay, let's look at the next one. Okay, so here I took called, and I went a generation further, spread out. So it's similar to the slide before, but the yellow dots, which were there on the slide before, are now extended. Their neighbors are in this kind of dark green form. And you see, once again, these are all past tense forms. Some of them morphologically quite different. Laid, for example, here. Lay, laid. Keep, kept. Okay, so the point is, this is a way for us to discover what words have a distributional similarity, despite the fact that their ed form, their past tense form, is formed in some way other than adding the letters ed. Okay, here's some other examples. Just chose the word language. What words are close to it? Yeah, these don't seem to have a lot in common. Okay, here I did the same thing and then added another generation. And in fact, at this point, I think I was asking for, let's see, 7 nearest neighbors. So language is at the center, and then it reaches out to get 1, 2, 3, 4, 5, 6, 7 nearest neighbors. And well, what we see is they're all nouns, and they're not all singular nouns. I see powers and views. Okay, so here's a case. I chose made because it's one that's definitely not formed by adding ed to the base form. You take make, and the d somehow pops inside. It's not maked, but made. And what words is it closest to? And here I just chose the 3 nearest neighbors, and you can see these are forms created by adding ed, the neighbors. Here's the same thing, but adding another generation, so to speak. It's spreading outwards. Once again, these are all formed, many of them a regular way, and some, like kept, in an irregular way, morphologically irregular. Again, same thing, increasing the number of generations, therefore the spreading out of the word. Yeah, so here's an interesting geometry. It's interesting that as you extend from the core word made, and you look at the closest words formed and established, mostly their descendants form a kind of a interconnected graph. But the words around drawn, which are close to used, don't hook up with the rest. There's more things to think about with geometry, topologies like this. Okay, here's another similar example, which I won't discuss any further. Okay, here's a focus on just the nearest neighbors I've made. You see we've got these quite irregular past tense, such as brought, but also hold, held. Again, here's a single word with its 8 closest neighbors. Okay, so here's another case where people, of course, is the plural of person. What words are close to it? They're by no means all plurals. And this surprised me. It's not a good thing. It's not a bad thing. It just is. Okay, looking at prepositions now. So prepositions, unlike nouns and verbs, are high frequency words mostly, and they're in a small class. And therefore, the nearest neighbors, so if we start with and we look at its nearest neighbors here, I've chosen the 5 nearest neighbors, the blue, call that the blue generation. So the nearest neighbors to the blue generation are largely other members of the blue generation. Again, that will never be true for things like verbs and nouns. So this is a characteristic of these categories, like high frequency words. Here I've chosen, to follow up on that, I've chosen here a modal verb, would, as the seed. And so we see something similar here. The blue, the 5 closest words to would, you can see I've just experimented with a lot of different numbers about how many nearest neighbors to use. So here with 5, the nearest neighbors to the blue generation remain inside the blue for the most part. And then there are just a few words that move outside, like became and will and did. Okay. All right, on to some other stuff. Well, I was having a miserable time trying to get these videos up and running so I could show them to you. I showed you a couple of videos that I had made a bunch of years ago, and the issue was that I normally do all my work with Linux, and what we're talking about here is this program Gephi. It's a Java-based program. I mentioned it earlier, and they're using a real old version of Java, and it's difficult to get their system up and running under Ubuntu. And looking at the internet, a lot of people have the same issue that I do. So it was driving me nuts, and I realized, well, maybe I could try it on the Mac, because this is what I'm running Camtasia on. And it seems to be working fine. So here we are, and I would like to take a look at some of these videos with you. So what I'm going to show you here is Gephi, and this is the force-directed graphics. And so I want to explain to you what you're going to see. At the beginning, you're going to see all of the nodes, and I think it's 4,000 nodes, they're all in orange, and they're scrunched together in a small square at the beginning. It's like the universe just before the Big Bang. They're all scrunched together, and then boom, there's a boom, and every unit repels every other unit. But those that are held together by the threads, which are the edges of the graph, and those edges are connecting between each word and its k nearest neighbors, and I'll show you what you get for different values of k. So you have these threads which then hold things together. And so let's just take a look at what we see here, and I'll turn it on. Yeah, boom, it explodes. And so you see it with okay, so I turned up the darkness of the lines, and once I get the cursor close to it, it becomes bleached. I have no idea why. It's always been this way. So this is a large set of, I think, 4,000 words from English, from Encarta, and I can zoom in, and you see these grainy, these little tendrils and all. Those are the things whose grammatical functions we've been able to more or less pull out. So I can click on that T there, which will bring in the names. Each little word is tagged. I'm going to zoom in. I zoomed out for a second. I'm going to zoom in, click on the prevent overlap, zoom in some more, and the font is too big, so I'll lower the font, and yeah, there, and then make them a little bigger, And now we can read. We can read what we've got here. So what do you see? Give, make, maintain, establish, protect, create, promote, ensure, keep, allow, raise, improve, accept, indicate. Well, you've got bare forms of verbs, obviously. Retain, win. Okay, so we've got, so these units are, these words are linked to one another and they're morphologically closely related. Okay, I want to show you something similar for French. And so we'll start out in the same place where all the words are scrunched together before the Big Bang. And then we'll let it go. Let's see, here we are. Okay, we start off with that algorithm, run, and then bang, but it the scale was wrong, so you didn't really see it go boom. All right, we're going to zoom in. We'll see a little bit better. We're going to zoom in. And there's this little piece that's heading off, so I'm going to stop it before it becomes invisible. And let's zoom in to see these words are not connected to any others in the base galaxy. So we want to find out, what are they? We zoom in close. We turn on the text, and what are they? They're all 4-digit numbers. They're all dates. And over there, they're not dates. They are, what are they? We try to get them to not overlap so much. We blow it up. We lower the size of the font, and they are months of the year. Okay, so the months of the year, together with dates, this is from an encyclopedia in French, and Carta, so they are their own mini galaxy. All right, so we go back to the main galaxy, and you can see it looks quite different from the English. It's, most of the words are in tendrils, and there's very little stuff in the middle. So we've got these two blue dots. I made them big. I wanted them to see. So this is girl, it's a feminine singular noun, and this is woman, femme, it's a feminine singular noun. So the question is, are they surrounded? Are these words surrounded by feminine singular nouns? The answer is yes. We zoom in and make the words a little bit more visible. And yes, they're all feminine singular nouns. Theory and zone and version and notion and declaration and victory and situation and tradition and doctrine and civilization, community, communauté, famille, family. They are surrounded by feminine singular nouns. All right. Let's zoom out and look at something else. Okay. Now that is really interesting. Here we've got one of these. We've got a word that's linking. What could it possibly be? It is porte. P-O-R-T-E. How could that be? How could it be there linking up two completely different? Well, on the one hand, it's connected to what? To feminine singular nouns. And it is a feminine singular noun. It means door, la porte. But it's also connected to third-person singular present verbs, like demeure means to live, not to live, but live, and pass. These are third-person singular verbs here that they're connected to. So porte is ambiguous. It's both a third-person singular verb and a feminine singular noun. And we have loads of those in English. Here we've got these third-person singular verbs up there. We've got loads like that in English, with these ambiguous words. French has very few. And so it allows French to break up into these more or less independent, or rather independent, tendrils in a way that English doesn't see. English words are way, way, way too ambiguous. And this particular representation is built on the assumption that every word is a thing in and of itself, that the same spelling couldn't represent two different things. Okay, let's look at some examples here. This is kind of a random mess. We've got period, and we've got a couple of prepositions and a semicolon and the word that and another preposition or two. We've got where and some other complementizer, sentence introducers. These are grammatically words that don't have many equals. little bit more zooming in. What do we see down there? We see names of countries. We see France, China, Great Britain, Russia, Sweden. There's Sweden, Poland, Greece, Sweden. There's Greece. Mediterranean, Switzerland, Palestine, Norway. Okay. We zoom in somewhere else. Getting to the end. Now let's look down at that big tendril there. Have we looked at it yet? I'm not sure. Let's see, what do we see down there? We see plural nouns. And oddly, I find it odd, it mixes feminine and masculine. There are many contexts in which the two appear without any distinction, and it does not draw that distinction. I'm surprised. Once again, we've got a lot of plural nouns there. And getting to the end, what's over here? We've got names or adjectives based on names of country. So British, American, of the world, European. I can't quite read. National, Western. So adjectives based on geographic units. All right. Interesting.